Vidur, can you hear me? Vidur, roll number 133. Can you hear me? Okay, thank you.
Now, we are talking about scheduling algorithms. I know that there are three types of, actually four types of them. Can you tell me which are the four types very quickly? Which are the four types of scheduling algorithms? Long term, medium. We know that whenever a new process enters at that time, whether we are keeping it in the set of active processes, that will be decided by the long term scheduler. Should we put our process into the main memory? That decision will be made by the medium term scheduler. And once the process is in the ready queue, then should it change state from ready to running? That will be decided by short term scheduler. This we have already discussed about. Do you have any doubt in this? Which are the most frequently used scheduler? Which is the most frequently used scheduler? Short term scheduler. You are right. Short term scheduler. That is true. And we have also seen the diagram. I think sir has already completed the state diagram. And you are well aware about which states a process can assume and how it will be changing the states. So these are some of the measures which will be letting us know that how efficient a scheduling algorithm is. So turnaround time is the time when the process is submitted and the process is completed. Difference between that is known as turnaround time. Response time is the time from submission of the process to the first response. When it begins to receive the response, that is giving you the response time. If a task can specify a deadline, then how many deadlines are achieved? That will be decided, and our aim is to maximize the number of deadlines met. Then throughput is maximum number of processes completed per unit time. That is a measure which is from the system's perspective. This were from the user's perspective. Processor utilization, that for how much percentage of the time processor is busy. That is our processor utilization. And other parameters which are not exactly measurable, like performance related parameters are this. These are qualitative parameters. Quality will be ensured by this, that fairness, priorities, and resources should be balanced. Like if you are having some processes which are utilizing only CPU resources, but some process is also looking for IO, then IO might be given higher priority because IO will be used in parallel and then your CPU can be used. So based on the underutilized resources, we can choose the processes. Now, when I say priority, then scheduler will always give priority to the higher process over the lower priority one. That is obvious. We have multiple ready queue. If there is no priority based queuing, then there will be one ready queue only. And whatever policy we are adopting, there are several policies. We will look at them soon. But if there is priority based queuing, then there will be multiple priority. If we are going for n priorities, n plus 1, then starting from R0, R1 up to Rn, those many ready queues will be there. So first always this will be examined. If there is no process waiting here, then the next one will be examined. If there is one process here, then that will be given the priority. It will access resources of the processor. It will have the execution time. Once it is over, we will go to the ready queue 2, 3, and so on. In Linux, Unix related operating systems, 0 is the highest priority, n is the lowest priority. While in case of Windows, as the number increase, priority also increases. So that is okay. That is up to the interpretation and implementation of the system. But what we have to remember is in priority based queuing, multiple ready queues will be there. Now last time at the end of the lecture, someone asked that can we have just one ready queue in the priority? Can we have just one ready queue? So let us say that depends on the implementation. You can visualize your queue as the data structure. So which data structure do you think is better for this particular scenario that can be implemented? That decision can be taken by the operating system designer. So if you are going for, rather than if you are having multiple ready queues, then you have to start looking from the highest priority to lowest priority. Of course, here memory will be more utilized, but then the execution will be easier. If you are talking about just one queue, if you have one queue and all the priorities are kept in that, so whenever one process is coming, we will have to see that where to put the process. So you will have to scan that. You will have to scan and then appropriately you will be putting that. And apart from that, are you getting me? So can we say that is a trade-off between the scanning time and versus memory, something like that. So if the implementer chooses that I want to go for single queue, he can do that. But we are not sure whether that is a smart idea, because nowadays memory is hardly an issue, and this will be making the execution faster and quicker. And most of the time, rather than the resources as in memory or something like that, we are more focusing on the efficiency, because we want faster processor. We are going for faster processor because we want quick responses. So always we will be going for some additional cost if that is allowing us to go for efficient system. Now this statement are loosely made and they are not always true, but in general, in earlier days when memory was larger in size as well as they were expensive, at that time designers were worried about using memory liberally. But nowadays we know that memory is not much of an issue. What we are striving for is the process, and memory is also compact in size, so it is very easy to expand that and manage it. Now if we are going for priority based queuing, then one problem could be that low priority system will be suffering starvation if there is always high priority process present. Like let us say we are having in this queue some system, in this queue there are some processes, then there are processes, and here there is just one simple process who is waiting. Now before we complete this, again there is one process coming here. If there is a steady supply, steady input of the higher priority process, then this will feel starvation. Starvation means it is waiting for the resources but it is never getting the resources, and hence efficiency for this one is compromised. So what can be the solution for that? That we can allow process to change the priority based on the age or execution history. We can say that this process is waiting from last 1 minute, while these are just waiting for 1 second, 5 seconds, and so on. Then if it is waiting for 1 minute, then priority can be changed and it can be put to the upper layer. User doesn't need to do that. Operating system will take care of that if that type of scheduling algorithm is implemented. Or we can go for the execution history, that from this particular queue, last execution was done at this point of time. That means now it is time to change the priority and assign it a higher priority. If higher priority is slightly higher priority is assigned, if it is executed, fine. If it is not executed and still it is suffering starvation, then again we can make the priority higher. In this way, we can avoid starvation for the low priority system. So if we don't consider anything, then whenever there are many higher priority processes continuously coming in, then low priority process can suffer starvation. That is limitation of plain priority based queuing. Plain as in I'm saying the basic version. But later on, we can go for some changes like this, and then it will be fair to all. This is done to ensure fairness. Otherwise, your processor utilization might be maximum here. Your processor utilization will be maximum only because high priority processes are coming in. We are executing that. So processor is never free. But we also want to ensure fairness. So here where qualitative measure comes into the picture, and something like this can be done. I hope that we are all on the same page. Am I speaking too quickly? Should I reduce the pace and try to go a bit slower? Or you are comfortable so far? Karnav, roll number 44. Should I slow down? Okay. So now we are going to very soon start first scheduling algorithm. But before that, let us look at something interesting. Selection function will be there. Any scheduling algorithm always will have a selection function, and based on the selection function, it will make a decision that which process will go next. Selection function determines that which process is selected for the execution. It is like, let us say, when I am asking you a question in the class, if you raise your hand, then I have some selection function in my mind. What could be the selection function? One of them could be that whomsoever has raised the finger first, I'll ask him or her. Then my selection function is who has shown the interest first. It could be that. Another one could be, I'll look at your faces and see that if there is someone who is new and who has not answered in the past, then to encourage him or her, I might ask him or her. So at that point of time, my selection function is to encourage the new processes, to encourage the new faces, to build confidence in them. So that could be my selection function. Sometimes I might be going roll number wise. So that is my selection function based on one parameter which is assigned. So here, some of the parameters which decide our selection function, one can be waiting time. The process which has waited the most so far, that should be given the higher priority. If your waiting time is the function, that means oldest process will be first given the resource and so on. Then it could be time spent in the execution so far. You may see that how much time you already spent, and if you are near to completion, then we may give you chance. Or if you have not given execution time so far at all, then you might be given a chance. So it can be implemented either way. Then it could be total service time required by the process. Like if 5 of you are asking me a doubt, there is one doubt which I can solve within half a second, half a minute, let us say half a minute. And one doubt is very lengthy and will require explanation. Then I might first ask the person whose doubt is smaller. Then I'll go for the next one likewise. So that we can say that service time which is required by the process, if it is known well in advance, then we can make a decision based on that. Why do you think service time required by the process should be considered? It will improve which parameter for all other systems? If I'm considering total service time required by the process, then how will it help us improve the performance? See, one of them I think we can say, yes, it reduces response time. It reduces turnaround time for this. But something else, less number of processes will be in the ready queue now. Because what we are doing, the ones which can be quickly executed, we are executing them and completing the task. So now less number of processes will be there. And that process was going to take lower time anyway. So why to keep it in waiting and increase the response time for that? And throughput also will be increased. Exactly. Because if we complete the processes quickly, throughput also will be increased. So indirectly, these parameters will be affected. Now turnaround time, that is service time plus waiting time, or execution time plus waiting time. Or we can also say finish time minus arrival time. That is our turnaround time. And then there is something called normalized turnaround time. Just turnaround time might not give you, that will give you idea from one process perspective. But if we are going for normalized turnaround time, then how that is experienced, what is the relative delay experienced by a process? And if you find that for multiple process, you will also come to know about something else. that we will examine in one of the examples today itself. So normalized turnaround time is TR. This TR is turnaround time. Okay, this TR is not response time, it is turnaround time divided by service time. Or I can say TS plus TW divided by TS. Are you with me? If this TR is same as TAT, can I represent that? That is, what is TR? What is turnaround time? Service time plus waiting time. So can I say that service time is TS and waiting time is TW? So TS plus TW divided by TS. That will be same as this. So that is relative delay experienced by a process. Because let us say, if your doubt is consuming half an hour, you are coming to ask me for a doubt and that is going to take half an hour. So if I make you wait for 5 minutes, then your turnaround time is 35 minutes. 5 minutes in the waiting and 30 minutes for solving your doubt. So turnaround time is 35 minutes. But what is the relative delay experienced by you? That would be 35 divided by 30. Because 1 point something. And if it is almost close to 1, then there is a very good measure of the service provided. Because you will feel that only 5 minutes were wasted. 30 were given to you only. While in the other case, if one process was having service time of 5 minutes only, and if I'm making him wait for 30 minutes, then what will happen? Waiting time is 30, this is 5. So 35 divided by 5. That means 7 would be the normalized turnaround time. So of course that person would feel that relative delay is much higher, which will be given to that. So if normalized turnaround time is close to 1, then that is the ideal situation. However, it might not be possible to achieve 1 for all the available processes. Am I making any sense to you? Do you have any doubts? Any one of you? If there is no doubt, then let us look at something else. Now, we have to make decision that which type of selection function are we allowing. Is it preemptive or it is non-preemptive? Preemptive means it can be interrupted and someone else can be given the priority even if your task is pending. That is preemptive approach. In non-preemptive approach, once we are executing something, unless and until it is completed, no one else will get the resource. So there are two major categories of the decision mode. Either an algorithm would be preemptive or it will be non-preemptive. Like if you are coming to me, again I'm going for the same example. If you are asking me a doubt, and unless I solve all the doubts, if I don't attend to another person, that is non-preemptive approach. While another one, someone says that I just have a quick doubt, and if I attend it, I hold you for a while, I attend him, and then again I come back to you, then that is preemptive approach. So these are the two categories in which we can broadly categorize our scheduling algorithms. So in case of non-preemptive approach, once the process is running, it will continue until it is terminates. That until it terminates means until it is completed, or it blocks itself. Like it wants input or output, and if input and output is not available at the moment, or for some other reason, if it is blocking itself, then only it will go out of the execution state. Otherwise, it will be in the running mode only. That is known as preemptive approach. In case of, non-preemptive approach. In case of preemptive, currently running system might be interrupted by the operating system and it will put into the ready queue. So we have to now decide that when do you want to preempt, at any point of time or periodically we are checking, like we are checking after each clock cycle or each 5 clock cycle, whatever the you decide for is best for your algorithm, whether it is periodically or we are allowing preemption only when new process arrives. When the new process arrives, at that point of time we see, should we allow the preemption? That is also possible. Or we can go for interrupt as well. Like if someone is waiting for IO and IO was not available at that point of time, but now it is available, then it will generate the interrupt. And at that point of time, we can make a decision whether we want to preempt the system. So non-preemptive versus preemptive. Which one do you think is an attractive approach? Yes, all of you are saying preemptive. Why not non-preemptive? Why non-preemptive is, you are not opting for non-preemptive? You may unmute yourself and answer as well. Okay, if you want, you can type. It will take more time for all the process. That is true, but there is something more crucial and more worrisome as well. If you are going for non-preemptive approach, then there is a threat. What is that threat? Something, starvation. Yes, starvation. Then some process will be starving. If you are going for non-preemptive approach, then some process will, it will lead to starvation, because if there are very long processes who are given the higher priority, then they are continuously blocking the resources and they are not allowing other processes to execute the process. So starvation, non-preemptive process may lead to starvation. So preemptive approach is better in general. But then what are the drawbacks of preemptive processes? Can you think of some drawbacks or side effects of preemptive processes, preemptive algorithms? If we are choosing preemption, then what do you think are the side effects? Switching overhead, exactly, yes. At that time, you are not utilizing your resource just for execution, but sometimes we are going for the context switching also, because when we are switching from one process to another process, at that time you will be having PCB, process control block. Don't worry about that, afterwards we'll be covering that. So you will have to store that information there, that how far have we reached, when you come back next time, what you should do, then which process, the another process which you are going for, then from where that process is to be executed. After some time again, you will have to switch that. So switching overhead will be there in case of preemptive scheduling algorithms. So if we are going for preemptive, then we may increase the overhead. But then the advantage is we are preventing one process from monopolizing the processor. Just one is not having monopoly or the excess over the processor, but all will be getting their fair chance. That is why preemptive processes are preferred. So do you have to say anything so far? Otherwise, we are ready for our first scheduling algorithm. So now we know all the terminology, how to measure, and whether any scheduling algorithm is preemptive or non-preemptive. You should be able to classify that. Are we good to go for the first scheduling algorithm? Okay. Then the first one is first come, first serve. Fcfs. You might have heard that in the real life as well. And this is the approach which is taken in most of the real life scenario. Like if you're going to a mall, then you are going with a cart, whoever reaches the queue first, then you will be given first priority, then the second priority, then the third, and so on. So in that one also we have observed that in some of the places we have quick counters, that if you have lesser than 10 items, then you will be given the priority. Like, or you have a separate counter for that. So that is the priority queue or something like that. But otherwise, if there is nothing like that, then even if you have 10 items or if you have one item, then you will have to follow the queue. If you come first, then your billing will be done first. Then the next one, and so on. So each process joins the ready queue. Can you tell me what is the selection function here? Let me take you to the selection function. Yes. What is the selection function in case of Fcfs? How do we select that which job will be executed first? No, now I want you to answer me in terms of the parameters which you already learned. No, not lesser turnaround time. No, turnaround time we will not know, because we don't know waiting time. Yes, waiting time. That is true. So here the selection function, this we will discuss at the end, not now. Selection function is waiting time here. Larger the waiting time, higher your priority is. In the first come first serve, the only selection function is waiting time. Decision mode, what do you think? Is it preemptive or non-preemptive? It is non-preemptive, that is true. It is non-preemptive. So each process joins the ready queue. Whenever current process ceases to execute, whenever it stops to execute, then we will see the process which has been waiting for the longest time, which is oldest, that will be selected. So maximum of the waiting time, that is the selection function, and this is non-preemptive. Whichever process is having the maximum waiting time, that will be given the resource. Which resource? Or processor. Execution time will be allotted to that. So now let us take one example. Please bring your book and pen. You should have a book and a pen with you. And I want all of you to calculate this, and I'll ask any one of you to answer it. So now we are saying that we have divided some time unit, that A process arrives at 0 time when we are just beginning. Then B process arrives at 2, then it is arrives at 4, 6 and 8. We can also say that this is, let us say, our clock, that when we have just started, this has come. Then after 2 clock cycles, this has come. Then after 4 clock cycles, this has come. Or you can say unit time, doesn't matter. Whatever is the unit that we are not bothering about. So there are 4 processes, 5 processes. We are naming them as A, B, C, D, E. And this is the arrival time. Service time is that how much time unit is consumed by A. So A arrives at 0 time and it is going to take 3 time slice. For 3 time units, it will be executed. Then it will be over. When it is over, at that time, can you tell me how many processes are, please write this table in your book first. I'll give you a minute. Write down this table in your book. Please let me know when you are done. Okay. So now we want to draw a chart. We want to draw the activity diagram, something like that, that how the CPU is executed. So from 0 time to 1, 2 and 3, for 3 time units, A will be executed. Yes or no? Yes. Then at 3 point of time, do we have any process ready which is already in the ready queue? Is there any process available when A completes the execution? Yes, we have the process. Which process is that? B. B is there. So B's execution will start at 3 and then it will end at 9. Yes, it will end at 9. It will end at 9. So now when it ends at 9, it is having 3 processes available. C, D and E. It is having 3 processes available. So which one will be given the priority? Process C, because here it is very simple. It has been waiting for the longer time. It was waiting from 4. So it will be given the priority. So it is something like this. Okay. This is our table that at 0 point, at 0 time A came, then for 3 it is available. Then B takes 6. So here it is 6. These are just unit 5, 10, 15 to give us the rough idea where we have reached. So at 9, B is completed and C will be started. C is taking 4 units. So next 4. So at 13, C will end. Then D will take over. Then 13 to 5. 18, it will execute and at the end, E will be given the execution and is 20. If we look at this, then service time is 20 and at 20, we will have completed that. So now can you answer me that if service time is this only, okay, service times are same, processes are same, but if I'm changing the arrival times, will they complete at 20 only, or that may change? They'll complete at 20 only if I change the arrival times. The first and third columns are same. I'm changing the second column. The middle column, I'm changing some of the values. Then do you think this 20 will be changed? No? Okay. So let me, yes, it might change. It might change. Depend. Yes, exactly, Ronak. If the processor is idle, then it will not be ending at 20. Like here, instead of 2, I'm saying that B arrives at 4. It arrives at 5, and so on. I'm saying that B arrives at 4, then 5, 7, and 9. Then what will be the change? 4, 5, 7, and 9. I'm just incrementing this 4 by 1. Then can you tell me at what point of time all the processes will be completed? 21. True. Then it will be completed at 21. So even though service time was required by all the processes is 20 total, but here we will complete it 21, because in between processor was idle for some time, and processor was idle not because of some other reason, but because due to absence of any available process. If that may happen that this one is at 4, and then these are at 18, 18, 18, 19, and 20, something like that. If they come together afterwards, then again it will be changed. Anyway, you don't need to calculate that. Now, if service time is different, do you think that will affect? And now I'm keeping first two columns same. In third column, if I'm changing, total is still going to be 20. Okay, total is 20 only, but here I'm changing the service times. Then will we complete the execution at 20, or that might change? Let me repeat the question. First and second, those columns are same. In the third column, I'm changing the times. However, total is changed. Total is same. Total is still 20. So it might change. That is true, it might change. Can you give me the example where there is a possibility of it? Give me one example, one of you, that how will it change? Yes, if A is 1, exactly. If A is 1, and that I'm making here 7, if it is 1, 7, 4, 5, 2, then total service time is still 20. But from at 1, A has completed and B has not arrived. So in this case, even though service time is same, our total completion will be different. So there are many parameters which will be affecting the scheduling, your throughput, response time, turnaround time, efficiency, CPU utilization, so many things. It is not a black and white story that this one affects this only. Indirectly, there might be impact at many places. So if first come first serve is clear, and which I believe it is, because it is very simple in nature, can I ask you to find out response time for all the processes and turnaround time for all the processes? Please make a table and find out response time for all 5 processes and turnaround time for all 5 processes. And do not reveal the answer until I ask you to do. Just let me know whenever you are done, so I know how much time to give you. Turnaround time and waiting time. Response time, rather, response time. Response time. Okay, others, is it done? Okay. So now I said waiting time first and then I changed it to response time. Do you think waiting time and response time are same? Is waiting time and response time always same? Yes. Yes, in this case they are same. In this case, waiting time and response time are same. In which time it will, in which type of algorithms they will be different? Waiting time and response time, they will be different in which type of algorithms? In preemptive. In preemptive scheduling algorithms, waiting time and response time will be different. Here they will be same because once it starts, then it would be completed only in normal scenario. While in case of preemptive, waiting time will be larger than response time or smaller than response time? Usually larger, same or larger, never smaller, same or larger. Okay, fine. So this is just to tell you that how they will start the execution and that. So finished. Are you getting this turnaround time? Please check your answer. Is your turnaround time this? If it is different, you can ask me. Because sometimes I'll have intentional wrong answer in the table. So you don't need to agree with me. You need to tell me that here it is incorrect. So finish time of the processes are this and turnaround time are this. Now, can you also find me please normalized turnaround time? For all the processes, can you please find me normalized turnaround time? Are you getting this? The last one is turnaround time. Normalized turnaround time. Normalized turnaround time is turnaround time divided by the service time. So here turnaround time is 3. Service time is 3. So 3 divided by 3. Here it is 7 divided by 6. 9 divided by 4 and so on. So what do you think is the minimum possible value of normalized turnaround time? 1. And what is the worst possible value of turnaround time? I mean, not in this scenario, in general. I mean, what can be the worst? How are you saying service time? See, here service time is 2 only. And here it is 6. Infinite. Worst could be close to infinite. Larger, the worse. Okay, larger, the worse. And what is the best value possible? The best value of normalized turnaround time, 1. Minimum value is the best value in this scenario. If it is 1, that means it didn't wait at all. It came, it was given the resource and it was executed. No time was wasted. 1 is the best possible value and larger the better. So here this process would have felt, unjust in a way, because it just wanted 2 time units on the processor and it had to wait so long to get that. But most of the time, we also look at mean of that and then to decide that how much time we are waiting. So turnaround time mean here is 8.6 for this. And this normalized turnaround time mean is 2.56. If you add this 5 and divide by 5, you should be getting this. Please verify whether these are mean. 3 plus 7, 10, 19 plus 38. 19 plus 24 divided by 5. Please check out if you're getting this. So sometimes for a particular type of system, if your data is likely to be this, and then we will be going for several examples, and two routing algorithms can be checked. We can find out various measuring parameters and try to see mean. And based on the parameter, we can say that which routing algorithm is better for this type of data, and so on. See, this we are learning from the perspective of single processor. Okay, here we are not even involving complexity of the multiple processor. We are just going for single processor where multiple processes are there. In almost all the realistic operating systems, you will be having multiple scheduling algorithms running together. It is not that they are following Fcfs or they are following something else or they are following third algorithm. It is not so. Based on the situation, based on the number of processes present, based on how which type of processes are present, it will be deciding which algorithm might be chosen. And multiple algorithm might be chosen as well, like combination of two, hybrid, or after going for the, let us say you might have priority based, but again in the priority based, if there are 5 processes at the same priority, then which one might be chosen? It could be first come first serve, it could be shortest time which is asking for, we may give resource to that, it could be round robin. Round robin means one by one all of them will be given turn, or so. Anyway, don't worry about that, I'm just trying to give you perspective of that this we are learning very basic to understand. It is not implemented in the operating system as it is. However, these measuring parameters will certainly play a role in deciding which one is good. So can you think of any issues with Fcfs? First come, first serve. Any problem with this? One process at a time. That is okay. See, always you one process at a stretch. That is what you mean by that, Ronak? That one process at a stretch. At a time, there will be always one process only. At a time, there will always be one process. But at a stretch, there is one process. So for no, here we are Rishi. We are not going for long. Yes, if there are too many long processes first, then the shorter one, if it is new, it will feel starvation. That is true. That is true. Yes, there is no priority here. There is no priority here. Urjit, CPU utilization not necessarily be low. CPU utilization will not be low because whichever is present, always it will be executing. So CPU utilization is very good here actually. It will not be low. But here priority is not assigned. See, whenever priority is not assigned, or if all of them are at the same priority, then only first come first serve will be executed. So here we can say that starvation for the smaller process if there are too many longer process before that. Yes. So a short process may have to wait for very long time before it gets executed. And why we are emphasizing on the short process? Long processes also will have to wait, but impact on the long process will be slightly lesser. Let us see this example. There are 4 processes, W, X, Y, and Z. Arrival time is 0, 1, 2, and 3. W and Y are tiny processes. They just want one time slot. And X and Z are the monster processes which require 100 time units. W starts at 0, it will complete at 1. When it completes at 1, then X is already present. So it will start, it takes 100 units, so it will complete at 101. When it completes at 101, then 2 was already present. Y and Z, both of them are present. But Y being the old process, it will be given the priority. It will start at 101, it will end at 102. Then at 102, the last process will take over and it will end at 202. If we look at the turnaround time, then turnaround time for W is 1. For X, it is 101. Finish time minus when it has arrived. So it is 100. For Y, when it is completed 102 and it arrived at 2. So it is 100. For Z, it was completed at 202 and it was present from 3. So it is 199. So normalized 1, for this it is 1, for this it is 1. What is the normalized turnaround time? Turnaround time divided by service time. So 1 divided by 1, 100 divided by 100. Here it is 100 divided by 1. So it is 100. And turnaround time 199 divided by 100. So it is 1.99. So which is maximum suffered process here? Why? Even though Z was the newer process, but because Y was a shorter process, impact on that is higher. So that is why we say that the process which is shorter, and if it has to wait for the longer duration, then that is a bit problematic. Because Z also had to wait, but Z આપણે કહીએ એને વસૂલ કરી લીધું છે આટલો બધો ટાઈમ લઈને in a way it has ensured to go for the normalized time for 1.99, which is a decent measure. So I hope that all of us are together so far. If you are still not clear with the parameters, I urge you to go through that. Please learn very clearly what is response time, turnaround time, what is waiting time, what is execution time, what is normalized time, fairness, etc. Please go through them. And also try to understand that which parameter we should try to minimize and which parameter we should try to maximize. Can you tell me which parameters should be minimized? Like, yes, normalized turnaround time should be minimized. Turnaround time also should be minimized. Then response time also should be lesser. Lesser the better. That is true. Can you think of any parameter which should be maximized? Throughput. Yes, throughput should be maximized. What is throughput? Throughput is how many processes are completed in unit time. That should be maximized. So if more number of processes you can complete quickly, your throughput will increase. So throughput should be maximized. Then which is the other parameter which we want to have larger value? Service time actually we don't decide. Service time is based on the how long or short the process is. That is requirement of that. CPU utilization, yes, we want CPU utilization to be larger. And then deadlines, we want to achieve maximum deadlines. So here we have already seen that normalized turnaround time for Y is 100 times the service time required. Service time required was 1 only, and it is more than that. So of course it is not something which is desirable. So in case of, okay, read it first and then I'll explain. Do you know the difference between IO bound process and CPU bound process? Are you aware of difference between IO bound process and CPU bound process? Can you hear me? Yes. So if you don't know, that is okay. તમારે ના પાડવાની. ઓકે, પૂછવું એટલે હા અથવા ના એવો જવાબ આપવાનો. તમે જવાબ ના આપો એટલે મને શું લાગે કે નેટવર્કમાં કંઈક ઇશ્યુ છે અથવા તમે લોકો બધા ભાગી ગયા છો. So anyway, you are right. When we say CPU bound process, then If any process is spending maximum time on CPU, then that is CPU bound process. If any time is spending maximum time on IO, then that is IO bound process. Let me give you example. If we are talking about Linux, then if we are interacting with the Linux terminal, we are writing ls, we are writing something, then you are executing some commands, and then accordingly your operating system gives you response. So the Linux terminal, we can say that is an IO bound process. That will be an IO bound process. Now, if you are going for any deep learning or machine learning algorithm where you are going for training the data, at that time, for very long time, your CPU will be busy with that. So that type of process we can say is CPU bound process. So if the process is spending maximum time on CPU or processor or processing the data, then that is CPU bound process. And if any process is spending maximum time interacting with input or output or both of them, then that is IO bound process. Is it clear now? Yes, computation. If you are spending more time on computation than taking or putting data, then that is CPU bound process. Like if you're talking about Linux terminal, the example I have given, when you go for ls and when it is showing you the data on your terminal, so input will come into the picture, output will come into the picture, and then processing time is very less in that scenario actually. And I hope we are well aware that processors are super fast. They are fast. IO will be slow. IO will be much slower as compared to our processor. So the systems which will be interactive system with the user or which are using frequently IO, then they will be IO bound process only, because processor they'll be having very less time on, because processor will be very quickly responding that. But most of the time they are spending on taking the input or displaying the output. Is it okay so far? Then we will talk about these points. Okay, so now here it is saying that first come first serve, it favors the CPU bound processes. How? That IO bound processes will have to wait until the CPU bound process completes. Even though it is in the ready state, one process which is spending more time on the CPU, if it is already taken, then it will have to wait there. Now, whenever your CPU bound process is completed, then next IO bound process, if it is in the queue, it will come. But very soon it will be blocked. Why will it be blocked? Because IO operation will be very slow. So it will be blocked. It is blocked. And now what is the status here? That IO is being executed, but it is blocked. So unless you have given the provision of putting that in the ready queue and then giving priority to the other process. But if you strictly gone for the non-preemptive approach, then IO is blocked for input and output operation, and the next process which is probably on the way, that is CPU bound, but that is not given the priority, that is not given the resources, not priority, that is not given the resources, because currently we are going for only non-preemptive algorithm. So IO taken over, it has executed CPU for a little time and now it is blocked. But next process, even though it is wanting only CPU, it will not be executed, and CPU utilization will suffer in this case. So this is some issue with pure Fcfs strategy. When you are saying that one comes, it has to be completed and then only another can be given the resource, then something like this may take place. Because let us say, if we are talking about the interactive user only, that user is given something, then it was processed within nanoseconds and it was put on the output. Now user reads from the output, it gives another command, something like that. It might be in the blocked state. And meanwhile, another CPU bound processes also will be blocked. They will be in the waiting. So this is the issue. It is not a very attractive policy in the pure form. In the basic form, it is not an attractive policy. It can be combined with some another policy to achieve benefits of both. First come, first serve can be combined with priority as well, where we can say that we are assigning some priority to some levels and then we are going for first come, first serve, something like that. So that is the conclusion. If you have any doubt in first come, first serve, Please ask me. Is it all clear? Okay. Fantastic. We all are smart. I am a good teacher. You are great learners, and we don't need any questions, any answers. So this is pretty attractive. I don't know whether I have told you or not. Always in the GATE examination, there will be one question related to scheduling algorithm. Okay. There will be one question related to scheduling algorithm in 1 or 2 marks. So this is a topic we shouldn't want to miss if you are going for GATE examination. And even it is very interesting as well. And in general also, we need to know scheduling algorithms very well to understand the operating system. So please be with me until we complete this chapter. Then we will see what to do with the next chapter. I'll end the session now. Thank you.